This is the second part of the chapter, activation or inactivation of biological active molecules. So in the last video, we learned about the four major mechanisms of inactivation. So in this video, we will learn about those mechanisms in more details. Okay, so let's just start. First, mechanism of direct inactivation. So what happens? We already know the antibodies which work by this mechanism, that is direct inactivation. How they do it? These antibodies, they may block the active site of a biological active molecule or alter the conformation of the molecule so that it's get inactivated. Okay, so and usually the biological molecules, okay, they have usually have one site, okay, and that one site is necessary for their function. That means the rest, that one site is not that one site is actually, if you compare with the whole the total size of this molecule, usually that one size is actually quite smaller. Okay, so in case of direct inactivation, such as for example an enzyme, okay, the enzyme is, such a for so for example, suppose an enzyme which has an active site, okay, and this active site is localized in a small area of the whole molecule. So an antibody, okay, if it binds uh, near this active site, okay, it may block the reaction. How? Because when this antibody bind near that active site, the substrate of that enzyme cannot bind with that enzyme. So if it cannot bind with the enzyme, the reaction will not occur. Okay, so I mean sometimes it happens, it may happens because of this. When the antibody binds near the active site of the enzyme, it alters the structure, the conformation of the enzyme in a way that it can no longer bind with its substrate. Okay, so that's why it is called direct inactivation. The antibody is directly inactivating the a biologically active molecule. Okay, and there are several factors which can affect the direct inactivation, and which are the site of antibody reaction. Where the antibody antigen reaction is occurring, the ratio of antibody to antigen. How much the amount of antibody and antigen. Okay, the strength of antigen antibody binding, and the biological property of antigen. Okay, so this was about the direct inactivation. Now indirect inactivation. Okay, so what happens in this case? In vivo, that means inside the body, antigen antibody complexes are rapidly cleared by the reticuloendothelial system, okay, due to the formation of aggregated fcs of immunoglobulin G or fixation of complement. So we know that the immunoglobulin, they have the Fc part in their structure. Okay, so what happened? In this case, after the antibody bind with the antigen, okay, that means bind with the antigen. Okay, so which antigen? Which antigens is going to be inactivated. Okay, so the antibody binds with the antigen, and this antibody antigen complex, okay, and they cause aggregation of fcs, or they may cause fixation of complement. So that's why eventually they will be get phagocytized by macrophages. Okay, so why macrophage can phagocyte this complex? Because macrophage has receptors for aggregated fc or c3b, that is the complement. Okay, okay, so and so in this mechanism, okay, because of this one, say one antibody which cannot directly neutralize a biologically active molecule, but although they cannot directly neutralize the biological active molecule, but they can make them inactivated, okay, because of their destruction. Okay, okay, then another mechanism of inactivation, receptor modulations, and in this case the antibodies may block or induce changes in the cell surface receptors. Okay, so for example, some hormones like insulin, estrogen, okay, they work through cell surface receptors. Okay, so what I mean like for example, insulin work on cell, and the cell, they have receptors for the insulin. So insulin, I mean specifically can bind with that receptor. So the cells which have receptor for insulin will work only for those cells. Okay, the cell which lack receptor for insulin will never bind with them. Okay, so anyway, so for in this case, the ability of cells to respond to activating stimuli may be lost because of reaction of antibody with the receptor. Okay, and antibodies to cell surface receptors may occupy the receptor. That means cause steric hindrance or may induce endocytosis, stripping, or structure alteration of the receptor. Okay, that means receptor loss. So actually, what happens in this case? The antibody is not acting on insulin. Rather, antibody is acting. That means inactivating the receptors of insulin. Okay. I mean, say for example, the muscle cell. Okay, they need the insulin because when insulin bind with the muscle cell, this cell can then start. Start absorbing the glucose from the blood. But if so, okay, so that means this cell actually have receptor for the insulin. Okay, that's why insulin can bind with these cells. So now think that some antibody, they bind with this receptor. I mean the cells which need to bind with the insulin, but antibody binds in the receptors, in these receptors. So as antibody is bound with the receptors, insulin cannot bind with that receptor. That means insulin cannot bind with that cell. Okay, so thus the activity of insulin get reduced or inactivated, right? So as insulin cannot bind with the cell because of the antibody, work will not happen. Okay, so this is called receptor modulation. Okay, the receptor get modulated, not the biologically active molecules. Okay, then another mechanism of inactivation, ADCC, antibody dependent cell mediated cytotoxicity. Okay, so in this case, the antibodies reacting with cell surface receptors may induce the infiltration of inflammatory cells that secondarily destroy the receptors. Okay, that means first the antibody binds with its antigen. In this case, the antigen is receptors, and after this complex they attract the inflammatory cells. Okay, infiltration means that as they attract the inflammatory cells, these cells come there. Okay, and such as for example natural killer cells. Okay, so the natural killer cells, they can come to the scenario, and they can eventually cause destruction, okay, of that receptor. Okay, because natural killer cells, they can recognize the FC receptors of the antibodies which are bound to the target cells. Okay, okay, so we are done with the inactivation. Now I'll talk about the activation of biologically active molecules. So what happens? I mean, we know what activation. So when activation of biologically active molecules occurs, it enhances their biological function. Okay. So I mean, because of activation, the biologically active molecule, they get more active. That means their functionality increases. Okay, and also there are different mechanisms by which the activation can occur. These are the mechanism: conformational stabilization, increased binding affinity, receptor selection, buffering, and receptor activation. Okay, so let's see what these are. I mean, let's try to get some more information about these mechanisms. First, conformational stabilization. So what can happen? In this case, the conformation, the structure of the active molecules will be more stable. Okay, so what happened? The antibodies, they may directly bind with the hormone, but away from the active binding site of the hormone. I mean, in this case, the antibodies who are causing the activation, they don't bind in the active site. Rather, they bind in a different site. Okay, So and cause the activation. So for example, beta galactosidase. Okay, it's an enzyme. Okay, and this beta galactosidase, it can exist in two form: inactive form or active form. Okay, that means they have two conformation. Inactive, I mean, in one conformation they are inactive, in another conformation they are active. So there are some antibodies, okay, which can bind to the beta galactoside. I mean, not in the active site. Okay, they can bind in a different site than the active site of the beta galactosides, and after and this binding can change the conformation of the beta galactoside to active conformation. Okay, so suppose the beta galactosidase, it is in its inactive form. So the antibody will bind with the beta galactosides and change the conformation of beta galactoside, which conformation will be active. Okay, that means in this case the antibody, they are stabilizing the structure of beta galactosidase towards the active conformation. Okay. Okay, I mean, in this case, actually, what happened usually, like the enzyme. Okay, uh, what's the function of enzyme? They do I mean, they do catalysis. So, I mean, if catalysis want to occur, the substrate, okay, it need to bind with the enzyme, and this binding happens in the active site. So when the enzyme, suppose the beta galactosidase, is in its inactive form, the active site is non-functional. I mean, the substrate cannot bind there. But after the antibodies, they bind with the beta galactosidase. The change of the conformation of the beta galactosidase changes, and the active site, I mean, its structure changes in a way that now the substrate can bind there. Okay. Okay, it was one mechanism by which activation can occur. Then another mechanism of activation: increased binding affinity. That's the binding affinity of the biologically active molecule get increased. Okay, so what happened? The antibodies, through cross-linking the molecule, may increase the affinity of binding and the activity of a hormone. So, for example, EGF. Okay, endothermal growth factor. It's a biologically active molecule, and this growth factor plays an important role in the regulation of cell growth, proliferation, and differentiation, etc. Okay, so to do so, the EGF, okay, this factor have to bind to specific receptors. Actually, the cells, they have specific receptors for the EGF, and that receptors are called EGRF. Okay, EGF receptor, epidermal growth factor receptor. Okay, and in vivo experiment showed that EGF bind to the antibody increase the growth of fibroblast. I mean, if okay, fibroblasts are a kind of cells. Okay, so EGF can increase the growth of fibroblasts. Okay, so if I mean, the fibroblasts, they have EGFR, so that's why EGF can bind with them and cause their proliferation growth. However, some in vivo experiments showed that if antibody, I mean, if some antibody, they are bind with the EGF, the growth of the fibroblast increased. Okay. Okay, so then another mechanism of activation, receptor selection. Okay, so what happens? The antibodies may be able to redirect hormone binding from one receptor to another. Okay, let's talk about an example. For example, human growth hormone. Okay, there's several human growth hormones. Okay, so the human growth hormone has at least four distinct epitopes. Okay, how we know that? By monoclonal antibody. Okay, so anyway, human growth hormone, they has at least four distinct epitopes. Okay, and a given antibody may enhance binding to one site while inhibiting binding to another site. Okay, so in this way it blocks one activity while increasing another activity or redirecting the binding to a different site. So what it means, so for example, the human growth hormone, it has four distinct epitopes. Basically these four epitopes may have four different function. Okay, so the antibodies which activate this hormone, by receptor selection, what can they do? They can select some receptor. That means, say it has 4 receptor, so the antibody will bind with 2 receptor and inactivate them, and thus the other two, they will get more activated. That means their activity will be enhanced. Okay. Okay, another mechanism of activation, buffering. So what happens is buffering. Antibodies may protect a hormone from degradation and prolong its activity by by allowing slow release on the bound hormone. So the hormones. All the hormones, they have a specific function. So once the hormone do their function, they get degraded. They get degraded rapidly by the enzyme. But in some cases, this degradation can be delayed. Okay, because of some antibodies. So what happens? So some antibodies, okay, they can bind with the hormone and protect them from enzymatic degradation. Okay, so this is called buffering. Okay, so for example, superactive form of insulin appear to be protected by binding to serum albumin. Okay, serum albumin, definitely it's a protein. So if serum and albumin bind with insulin, that insulin, they can get superactive. Superactive means the insulin should be degraded after they did their work. Okay, but if serum and albumin are bound with the insulin, they don't get degraded. That means they keep continuing their function. Okay. Okay, another mechanism of activation, receptor activation. So what happens? An antibody may directly bind to the receptor for a hormone and activate the cells. Okay, so let's see the example. Say antithyroid receptor. Okay, so antithyroid receptor, because the antibody binding site mimics the structure of the activating ligand for the receptor. Okay, basically in this case the antibody bind with this receptor. Why? The structures are similar. Okay, similar with whom? The ligand which was supposed to activate it. Okay, the binding site is similar, like the ligand binding site between the ligand bind between the original ligand and the antibody who is causing the activation. So it's like when the ligand bind with the receptor, then it should get activated. The cell should get activated. But what happens? Some antibodies, they can bind in that receptor and make it. Can cause activation. Okay. So, okay, so that was all for activation, the mechanism of activation. So we already learned about the mechanisms of activation and inactivation. From the in the next videos, we'll we'll learn about some specific examples. Okay, such as insulin hormone, in case of insulin hormone. Okay, thyroid hormone, etc. So, see you in the next video. Till then, be safe. Thank you.